Hi class, in this video we're going to go over what recursion is. And I have got a XKCD comic here. It's a riff on recursion, and so it's a person asking what they're looking at, and they're looking at a picture of themselves, and within that picture of themselves, they're looking at a picture of themselves, and that goes on and on and on and on. And so this is a riff on a programming concept called recursion that we'll learn about today. Okay, so what is a recursive function? Well, a recursive function is any function that calls itself. And all recursive functions need a base case. And if we think back on that XKCD comic, there has to be a point where the function stops, or like the last image of that person looking at themselves. And that's basically where our recursion would end. So we need the base case to specify that. Base cases are often a known and simple solution, so that's usually what you would use for a base case. There are certain types of functions that are well suited to using factorials, and a lot of this recursive functions, some of it can be, you could rewrite a, say, iterative solution, like something you could do with a for loop using recursion. But there are some things that you can't do with iteration that you have to do with recursion. So that's why we're learning about recursion here. So here's the basic structure of a recursive function in MATLAB. Of course, it has the same function header as any MATLAB function would, and that's function in a braces. We'll have the outputs we want to give. It can give more than one, but in this case, I've got one where it's only giving one output. The function name, and then in the smooth brackets or parentheses, we'll have our input. In this case, input is n. And this is just a sort of standard boilerplate template for a basic, and I say linear recursive function. I'll show you what I mean by that later, is that this will proceed in a linear fashion without branching. And this is the easiest recursive function to understand. And we always need a base case scenario. So the base case in this is if the input n were to be 1, we'll output the base case value. Else, what we'll do is we'll call our own function. So this function, my recursion, if it's not the base case, it's going to recall itself, but it's going to recall itself with n minus 1. So if I passed in 3, it would not be n would not be equal to 1, and it would call itself, and it would pass itself a value of 2. And this always is sort of the method, is where your function is calling itself, and it's sort of confusing. It's like, what is going on? Well, let's go through an example together. Okay, so here's a sample recursive function, and n equals 1 is the base case, and we have some output, and what we are going to do is we're going to call my recursive count of 3. And let's put our MATLAB compiler hat on, and if n is equal to 1, well, no, n is 3. This is not the base case, so it'll go in this else part of this if statement, and it will say output equals n, so n in this case is 3, and then my recursive count n minus 1. So what it'll do here, before it finishes running this function, it's going to call itself, and it's going to call itself with n equals 2. So now we're in this function, and what we will ask is n equal to 1? Well, no, of course n is 2. And it'll say, oh, else the output is n, so 2, and then it's going to recall itself, my recursive function, but now n minus 1 is 1, so it is going to call itself again. And now we're in the new function, and so we have if n equals 1, and in this case it is true. So we've reached the base case, and you have to reach a base case, otherwise it will infinitely keep calling itself. So output is 1, and it'll skip this else and actually finish the function. So this is the first time when we've done this recursive function call that we've gone through an entire function. Sort of all the other functions, my recursive count 3 and my recursive count 2, would be on pause. They aren't finished executing yet. But now we'll pass the 1 back up to my recursion count 2. And remember that it was in the middle of the code, it had put a 2, and then whatever this output returns, which is 1, so it's 2, 1, and then it'll finish my recursion count 2. It's going to pass up in the output to 1. And now recursion count 3 will finish its job. So it is concatenating a 3 with whatever the results of my recursion count 2 is. Of course, that's 2, 1. So the output of the entire function would be 3, 2, 1. And that's sort of the basic case of how recursive works. It will call itself and keep cascading down until it reaches the base case, in which case it'll start passing the outputs back up to the final initial function call, which was my recursion count 3, and give us the output. So let's take a look at MATLAB to see how this works. So here's our function in MATLAB, and what I'd like to do when I call this function, I'd like to watch it compute. Because if I just do my recursive count 3, I'm just going to get the answer, and I'm not going to really understand how in the world it got there. And this is the example we discussed before. So what I'm going to do is I'm going to set a breakpoint. If I save that, now I can see the variables. You see here in my workspace, there's these variables A and S, and I could even say, let's just do this for, so if I go back in here, remember this variable A and S, it will not exist in my function. In fact, I could just say n equals 6. You see that that is my workspace right here. But if I pass in my recursive count 3, you see that there's n, this variable n, in this function. But remember, this function has no access to the workspace. When I call this, it will assign 3 to n. So this n here has nothing to do with the n in this function. It's just a variable name. It could be anything. So the reason I'm setting this breakpoint is so that I can actually look at this function as it runs and watch how it's going to compute. And that should give us some insight into how this recursive function runs. So I'm going to run this. And now I'm inside my function. How do I know? Well, I've got this green arrow here, and that's the line it's executing. And if you look at this workspace here, that A and S and N was 6, remember? But now it's been reset to the value 3 because that's what this function will do. Any input, it will automatically reassign it to the names of whatever the inputs you decide to put in your function. Okay, so now that n is reassigned to 3, we're inside this and we're going to see, is n equal to 1? Of course it's not. I'll continue to step. It'll get to the else, and then it's getting to this output here, and it hasn't actually executed this line of code. So when I execute this line of code, it's going to really, you can sort of think about it as reading it from left to right. And it's going to start to do this concatenation of n, so 3, and then before it finishes making output, so before it even makes a variable output, it sees a recursive function call. You see it's highlighted here in the same color as my function, so I know that's correct. If for some reason you typed it with a lowercase c, it wouldn't match up here. So it's recursive count, of course. What it's going to do is say my recursive count is going to call itself, and it's going to say n minus 1. N is 3. But before it finishes making this output, it's going to go and call its own self. So let's step on this line. And you see what happened is we're back in the beginning, and n is 2. So we've actually left the call for my recursive count 3. We're not executing that function, we're executing itself, but now n is 2. Of course, we have not reached the base case, so I'll continue to step. I'll get to the else, and I'm again trying to assign some variable output. Now, output is not output. It's not the same output from my recursive count 3. It's just a local variable inside my recursive count 2. But it would not exist. It's not the same output in my recursive count 3. So I'll step here, and of course what it's going to do is call my recursive count, and it's going to say 2 minus 1, so it'll be 1. So I step here, and now I've left my recursive count 2, and you see here in the workspace n changed to 1. But now we've reached the base case. So now I will set an output equal to the base case. In this case, we said 1. And so here is the first time you'll see in the workspace that output 1 was created. And when I continue to step through this, now it's reached this end of the function. It's assigned output. It will pass that back to n equals 2. So then my recursive count of 2. So I'll exit this function. And now you'll see recursive. We're in my recursive count 2. So output no longer exists because it's been passed. But now this function can finally complete the line of code right here. Remember, it was like paused right here. It had put 2, and it's concatenating it with the output from my recursive count n minus 1, in this case 1, and remember that was 1. So when I do step, it'll create that output 2, 1. Now I can finish the recursive count 2, and it'll pass 2, 1 back into recursive count 3. So end, and now we'll step back in to our initial function call, my recursive count 3, and that is now I can finish this output, and it'll be 3, and what should it pass for my recursive count n minus 1? So take a second and answer that. And of course, it will get the 2, 1 from the my recursive count 2, and now it will finish this function and will return 3, 2, 1. So that's how a linear recursive function runs. The answer would be, in this case, you could probably see is, what if I did 5 or 5? And I've suppressed the break. So what will the answer be if I put this in? And you should see this. It will be, okay, 5, 4, 3, 2, 1. So there it is. So one simple example to see where recursive functions could be useful would be computing factorials. And so remember, factorial is just a number multiplied by the previous number. So 1 factorial would just be 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And what we're doing is we're seeing that there's a pattern here. So if I had any n number, factorial, it's really n times n minus 1 times n minus 2, and continue that down until we get to 1. So this is sort of the explicit definition, but how could we think of this as a recursive function? So let's think about it, and really this is n, and all of this is what? All of that, really, it's really I'm multiplying n times n minus 1 factorial. So that is the recursive definition here, is that it's itself times 1 minus itself factorial. So that is the recursive definition of the factorial computation. Now let's think about how we could do the code differently. So we could accomplish this factorial computation with a for loop. So we could just have sort of this base case here. If it's 1, we could just multiply it by 1, right? But let's say we had 2 factorial, so if n is 2. Now, of course, if n was 1, would it ever run this for loop? So take a second to think about that. So would it ever run the for loop if I called my factorial 1? And of course it would not, because 2, the start value, is less than the stop value. So it would not run this code. But if I pass in 2, it would run how many times? 1 time. And it would say output is out, so 1 times k, 2. So that would be 2 times 1, and that's 2 factorial. And of course, if I keep running this through, it'll do it for any n. So that's a pretty easy way to see computing the factorial, is sort of the iterative method. A little bit more difficult is to visualize how would we compute this recursively. So remember, the recursive function, it must have a base case. So here, this is the base case. So the base case doesn't have to be on top like the previous function I showed you. It could be on bottom. And it needs to have a base case output. But if it's not the base case, it will compute itself, my factorial 2, iteratively. Remember, this is sort of like n times n minus 1 factorial. So let's take a look at this code in MATLAB to see how it would execute. Okay, so here's this recursive function for computing the factorial in MATLAB. And I've done a little bit of tweaking here, so it's looking a little bit different than the function I just showed you. And what did I do? I did sort of a trick here that I like to do, and I make a sort of a Boolean right here. This is a Boolean. It's a true or false, and basically it's comments is 0. So I have a statement, and I like to do this. It says if comments. So remember, it just has to be true for it to get in this if statement. So if comments is 0, it will not get in here. But if I put comments as 1, it would get in here, and it'll display a string, which actually is sort of useful. It says start my factorial, and then it'll tell you what number n is. And at the end of it, so here's the regular code. Here's the sort of the meat of the code for our recursive function. I have my base case down here, and I have the recursive function call here. But at the end of each function, I'm going to also display end of that function. So I'll show you why that could be useful. And it's useful because maybe you don't, when you're debugging something, you want to have comments, but maybe later on, once you're sure your function's working, you don't want to have them. But so if I wanted to, I could say my factorial, and let's do 4. And what it did is it printed all these comments, and it says start my factorial 4, but it didn't end my factorial 4, but because it's recursive. So it started the 4th call, then it started the 3rd, then it started the 2nd, then it started the 1st, which is the base case, and then it started to work its way back up. So it ended my factorial 1, ended my factorial 2, ended my factorial 3, ended the 4th one, and then passed us back this 24. So that's kind of useful. If I didn't want to see those comments, over here I could put 0. And now it won't display any of these comments. And so it's a very quick way to sort of turn on or off comments, which is very useful when you're debugging. So I'll turn them on. And then what I want to do is I want to do this recursive function. And I'll do it 3 times because it gets kind of tedious to go through it a lot. But let's call this function. Oh, and I wanted to watch the function grow. So let's put a breakpoint. And actually, let's put a breakpoint right at the beginning of the real sort of the meat of it here, which is our recursive function code. Okay, so I'm going to save that. And let's try it again. So my factorial 3. Actually, I'm going to clear the display so you can see it better. So let's run my factorial 3. So we've printed our first line here. It actually should print out start my factorial 3. Now I put the breakpoint after it, so now we're here in the actual code here. We started my factorial 3, and is n greater than 1? Of course it is. So it will go to output, and it'll say 3 times, aha, it's calling itself. It's calling its own function, and it's passing n minus 1. So when I continue here, we'll leave the n minus, or the n is 3, and we'll be starting my factorial 2. So now n is 2. We'll continue on, and we'll say, oh, out is 2 times my factorial function n minus 1, which now is 1. I'll step here, and now we'll be leaving, and we're recursively calling or starting my factorial 1. So I'll continue on, and what we'll see is now n is 1, so we'll output the base case. So now we can finish evaluating our code, and what we'll see here is now we're ending my factorial 1, and we'll pass that 1 back up to my factorial 2. So let's step here, and now we see n is 2, and now I'm still on this line of code. Remember, we kind of left this in pause. We didn't finish computing out. Now it will, and it'll say, well, it's 2. So out is 2 times 1, which is 2. And then we'll continue on, and we'll display end my factorial 2. And it will pass that 2 back up to n equals 3 now. So we're in the my factorial 3 function call. And now it can compute n as 3 times the output, which was 2. So now out is 6, and we'll display n my factorial 3. Continue on, and we'll pass the user back the answer, which is 6. So that's how we would recursively calculate a factorial with MATLAB. So a little bit more complicated than the linear recursive functions we're doing are recursive functions that branch, and we call that a tree recursive function. And here's sort of the basic structure. And it looks similar to the previous version of our recursion, except for one minor thing. So of course, we always have a base case, except this time we call our own function, so we recursively call the function twice. So where before we only called it once, now this will call its function twice. And what that does is it'll set 2 different branches off. For each recursive function call, it will recursively call itself twice. So it gets a lot more complicated. Let's talk about a sort of common use of this, and it's the Fibonacci sequence developed by Fibonacci, and he wanted to model an idealized population of rabbits, where he said it's the number of rabbits from each month as the sum of the pairs from the previous 2 months, which is a lot of populating. So he started with 1, 1. Now the Fibonacci sequence is actually started with 0, 1, but he added up 1 plus 1 to be 2, and then he took the 1 and the 2 and added them together. He added the 3 and the 2, so this is the Fibonacci sequence. How can we think about this as a recursive way to count this instead of having to do it explicitly? Well, really, the nth Fibonacci number is really the n minus 1 Fibonacci number added to the n minus 2 Fibonacci number. So remember that 2 was equal to 1 plus 1. So the third one was, this would be f1, f2, and this is f3. And so really f of 3 is equal to f of 2 plus f of 1. So that's how we can think of this Fibonacci sequence recursively. So let's think about how we could code this iteratively first and then recursively. So the iterative function could accomplish this with a for loop, and where we have the previous 1 and the previous 2. And what we could do here is, well, this is sort of the base case. Iteratively, if n is less than or equal to 2, we know that the first 2 Fibonacci numbers are just 1, so we could just return 1. But if we want to calculate the third or any higher, what we're going to do is we're going to do our for loop here, where we'll step from 3 to whatever n is. And what we could calculate for this first time through the for loop is we say the output is previous 2 plus previous 1. So if this was the third one, we would be doing 1 plus 1, which would give us 2, which is our third Fibonacci number. Now, what we had to do is we had to initialize previous 1 and previous 2 before doing this loop. But of course, if we want to calculate higher numbers, what we're going to need to do is in this for loop, we're going to have to reset those values. So I would reset the previous second one to, I'd step it one up to previous one. And now previous one is this actual computation. And I can continue looping through here until I get to my Fibonacci number of n. Another way we could accomplish this is with our branching of our recursive function call. So this is how we would accomplish it with a branching function. And we, of course, have the base case where if it's 2 or 1, we'll let output be equal to 1. But then if it's not, it's my Fibonacci sequence n minus 2 plus n minus 1. And actually, these could go in either order. It doesn't really matter. It's just a linear combination here. But in this case, we said the n minus 2 recursive call first before the n minus 1. And that's the recursive function. So let's take a look in the code for MATLAB.
So here we have our function, and let's take a look at how this would run with the branching and how it differs from a linear branching recursive function. So let's say we called my fib and we passed it 4. So we want the fourth Fibonacci number in the sequence, and what it would do would see is if it's less than or equal to 2, which it's not, so it'll go ahead in this other part of the branch of the if statement and get into this else, and the output will start to be assigned to my fib n minus 2. Now before it finishes actually making the variable out, it's going to call itself recursively and n minus 2. So that would be, it would call pass n2 to my fib. So now we'd pass n2 to my fib, and we'd be in a different call of the own function. And now we are going to meet the if statement, and we'll pass out back up to the top level. So we're back in my fib 4. But remember, it was at this line of code right here. It has not finished evaluating. It just went down this first branch of the recursive function, and now it's calling my fib n minus 1. So that's my fib 3. And now we would be in my fib 3. And what we would see here is we would do yet another branch because we have not reached the base case. So in the third myfib function, it would assign a new variable out, and it would say myfib n minus 2, which would call myfib 1. Now we're less than or equal to 2, so we've reached the base case. So it would put the output as 1, pass that back up to myfib 3. But remember, it's still trying to make this variable out. So now my fib n minus 2 is really just represented by the number 3, but it calls itself recursively again, my fib n minus 1, which would be my fib 2. That is also the base case, so it would pass back up to my fib 3, 1. And now we can fully evaluate this line here. And of course that would be 2, and we could finish that function for my fib 3 call and pass the 2 back up to my fib 4, which had a 1 waiting right here, and now we can add the 2, and the answer for it would be 3. So the fourth Fibonacci number is 3. Okay, so now let's take a look at this myfib with the debugger. So I've set a breakpoint inside myfib function, and I'm going to call myfib 4, and I'm going to assign it to the variable a. So here's the function call, and I'll assign it to a. Now remember, I couldn't just run this in here because you cannot run a function. You can run scripts, you cannot run functions. One thing maybe I haven't stated up to this point, and if you look in your current folder, you can actually see things that are function will have this little f of x next to it, and scripts will just have this little page with the MATLAB logo next to it. Okay, so let's run this function. And now I've passed it n equals to 4. So this 4 got assigned to the input variable n. And we are not at the base case, so we'll step in the out. And now we're beginning to build the output for the n equals 4 myfib function. But what it'll immediately do as it reads from left to right is see, oh, there's a recursive function call. So before it even finishes making out, so out is in the process, it's in the process of being made, it'll call myfib n minus 2. So we'll step into n equals 2. So we're basically now in a new function that we've called recursively, and n equals 2. And now this time we've reached the base case. So out will be set equal to 1. And we'll step through and pass that back on up. And you see now we're back inside the myfib4 function. However, we've only evaluated half of the assignment to out. There's another branch we need to go down, and that's myfib n minus 1, which is myfib3. So now we have n equals 3. So we're inside the new function. We still have not reached the base case. And now we're going to begin to build the output of myfib3. So the first recursive call will be n equals 1. So now we'll step into the myfib n equals 1. This case, we have reached the base case, so we'll assign that to the variable out right now. So you see now out is created. I'll continue to step through, and it'll pass on 1 back on up to myfib3. So now we're back in myfib3, but you see out hasn't been created yet. That's because we haven't finished evaluating this line of code. We've only evaluated up to here so far. So now we will evaluate myfib n minus 1, which is n will be 2. And we're now reaching the base case here. So we'll assign out to 1. And we'll pass that back up to n equals 3. And so now we can finish evaluating this line. So out is now going to be, we remember we got a 1 from myfib n minus 2, and we got a 1 from myfib n minus 1. So the output is now made to be 2. Continue to step, and it'll pass the 2 back on up to the highest level, myfib4. So now we've evaluated to here, and when I step through this line, it'll be 1 plus 2. So out will be 3, and then we'll pass on up the 3, and it will be assigned now to the variable a. So a will be equal to 3. Of course, that is the 4th Fibonacci number. So here's a classic error when making a recursive function. And so this is something you do not want to do, like reassigning the inputs of a function within the function. Of course, you never want to do that. You also don't want to do this when you're making a recursive function call. So this kind of looks similar to the myfib function that we just ran, but one of these lines of code is going to make it so this does not work. So take a second here, think about it, and come up with which line of code will prevent this from working. And the line of code is line 6. And the reason for that is that we're not storing this output. Remember above, we stored this output and passed it up as the output. So it should read out equals my Fibonacci n minus 2 plus my Fibonacci n minus 1. So we were missing the out equals. We were calling ourselves recursively, but we were never assigning the output to the function output. And this is a common mistake you'll see, and it's if you make it, don't worry, a lot of people have made the same mistake, but if you're not getting your output, that might be the reason, is you don't actually store the recursive functions calls.